We are ready to start, and I will get the questions on my screen. Okay. It's a question to Hitachi Energy. What are the advantages and challenges of the HKSiC MOSFETs?
Yeah, so we can take this. This refers to the paper that we published in your magazine, and is the technology that we are promoting and we are mastering here in with Hitachi Energy in Lenzburg, Switzerland. And it goes to improve the gate electric of the silicon carbide devices, to get a device with high dielectric constant, which has multiple advantages. On one hand, it helps us reduce the on state, the RDS on, but mostly it gives increased stability to the device, mostly through the fact that the gate dielectric has less density of trap states, which makes the device more reliable after many trips going positive, negative with high swings in gate voltage, and this is what we show also in the paper we publish and other journals. We show a very high robustness in many when we do experiments of really high swings of the gate voltage going deep into negative -15, which I think it's quite a lot for normal dielectric of silicon carbide MOSFETs, and this is what we see as the main advantage. On the challenging side, of course, is very difficult to find the good material, the good combination of materials. I'll have to say that that fulfill the purpose and have good stability and also a process stability, and this is what we are proud to share that we achieved, and we are promoting this technology.
Thank you, Virgiliu.
Yeah.
Okay, I have to be careful with my tongue, otherwise I bite on it.
Don't worry, I've been called in many ways, so you'll not be the first.
Yeah, I had in the time when I worked for Harris Semiconductor, I had a colleague in Somerville, and he was Polish, and his name was Jack Wojslawowicz, and nobody in the group in America was able to spell Wojslawowicz correct, and they only called him Jack W.
Yeah.
If you go back in old RCA data books, you find app notes from Jack.
Jack W. Yeah.
Jack W. Jack Wojslawowicz. Okay. Here comes the next question to Littlefuse. What is SMPD and its advantages? That's going to Aalok. Oh, Aalok, you need to turn on your micro.
Sorry, I was talking to my wall. So SMPD is an abbreviation or a short form coming from surface mount power device, so short form SMPD. This was a package which was pioneered by then Ixis, now part of Littlefuse, back in 2012. So there is also a press release dated 2012 regarding this particular package. So this SMPD is kind of a package which which bridges the gap between the small volumetric discrete and these high power modules. So something like a size of a €2 coin. So I have actually in my hand. So,
Yeah.
so it's like a very tiny package. And this package offers several advantages. So first is it is a DCB based isolated package. And therefore you have this classical DCB based isolation structure inside, inherent isolation. The package itself, keeping clippage clearance for the outer pin out and stuff in the mind, it can withstand minimum 2.5 kV RMS isolation voltage 1 minute. Then the DCB space, if optimized, this the advantage for this structure is to increase the power density, which is quite relevant in terms of the wide bandgap semiconductors, specifically to SiC. And also this being a surface mount package, it allows fully automated pick and place and standard reflow soldering process. So that is the quick, kind of recap and the advantages about the SMPD.
Thank you, Aalok. This question is addressed to Texas Instruments. As electric vehicles grow in popularity, there are demand in the market for automakers to make them more affordable. Can you speak to the specific benefits of GaN in this space?
Yeah, that's a great question, Bodo. So one of our missions at TI, and this is a corporate level mission, is to not just innovate in electronics, but also to look at how we can make more affordable solutions for the end customer. When we look at the automotive space today, a lot of the development is in 22 kilowatt OBCs. Historically, we're using lower power OBCs. And as we look towards the future, one-phase OBCs are going to be a place where people are going to be able to really adopt for a affordable EVs charging. And that's the place where we see that GaN brings a lot of value. When you increase your switching frequency, you're capable of heavily or significantly reducing the size of your inductors and transformers that you're going to be needing to use. One, that gets your physical size down, but the transformer inductors are probably two of the most expensive components that you're going to be using on a large, high-power electronics board. So when we're looking at that one-phase OBC, we're seeing 50, 60% size reductions by leveraging GaN to increase the switching frequency in, for example, our CLLC converter. We recently released a reference design with our GaN devices. We have a resonant frequency in the CLLC of 500 kilohertz, which gets you from a $30 transformer to hopefully a transformer that's under $10. And so maybe you spend a little bit extra on GaN, but that's a huge cost savings for the end supplier and what they're going to be able to deliver and make EVs more affordable.
That's a good move. And from my perspective, you have lower weight that had to be carried on from the electric vehicle.
Mm-hmm. That's another good key point. Weight, any kind of size reduction is going to help make the EV drive longer and hopefully save money in your heat sink costs, all the different components.
Thank you, Alex. Let's look what else we have here on questions. Back to Hitachi Energy. Is there a large usage of such high power SiC modules? What is the approximate ratio now and expected in the next years?
Yeah, I guess I can take that one. Yeah, I think it very much depends on different industries and different application. What is the ratio of this high power? So what we showed also in the paper that we published is 1200 volt and 3.3 kilovolt. And if we look at very high voltages, let's say 3.3, also going even higher, 6.5, 10 kilovolt, I think there we are still at the beginning. So we have the first usage. I think the very first one might have been in Japan, the Shinkansen train that uses the 3.3, but now we see more and more in terms of traction where power modules at these high voltages are used for sources of DC power, like batteries or fuel cells, hydrogen train, and so forth. So I think there it's still at the stage of a demonstrator or small series. So we are not talking about very large volumes, but the advantages and the development of cost of the especially the substrate, the epi wafer, and the improvements in defectivity rates. So we see this in the last years making really big steps. Goes into the direction of more large affordability for such technology. And then we see really concrete plans from a lot of our customers to go in the first series production in starting this year, next year, in the coming let's say very near future. Not anymore on academic level and just some trials in the lab or so, but really going into something that sees commercial use. So this is where, at least for high voltages, high power, where we are or how we see it now. And of course, as we go lower and lower in voltages, as colleagues also present 1200 volt and below, then there the percentage is much higher, and the use cases are more established. Yeah.
Thank you. We're ready for the next question. The next question is to Littlefuse. Why are the technical advantages of SMPD especially relevant for SiC?
Yeah, that's a good question. So traditionally, I mean, we know that SiC is meant for this high switching frequency application, and also typically having lower specific on-state resistance. We can expect that the current density or power density of SiC would be higher, much higher, as compared to the, let's say, silicon counterpart. So when we look at the SMPD package, so this PCB-based isolation structure and stuff. So there in the article, has been presented a concrete example wherein the SMPD was measured or compared against the standard discrete in terms of the performance. So first of all, this having the Kelvin source connection and the lower package inductance, one can expect that there would be an improvement in terms of gate oscillations, for example, or reduced voltage overshoots, for instance. And that was actually evident in the measurements which are presented in the article. So wherein we saw that if you compare the similar dice in the TO247 3-lead standard discrete and the SMPD, the same dice, then it was observed that the gate oscillations were eliminated in terms of, I mean, when we talk about the SMPD, SiC. Then second good observation was reduction in the reverse recovery time for the same dice. So basically, this improves the diode losses performance, and at the end, it improves the system level efficiency. So these advantages were quite evident from the measurement carried out. And as I said, this is the high power density package. Also, reliability point of view, or better power or thermal cycling point of view, this would be quite an interesting package when it comes to the silicon carbide applications.
We are ready for the next question. The next question is addressed to Texas Instruments. One of the key benefits of GaN is its ability to make technology smaller and more efficient. What are other application areas TI GaN has been successful?
Mm-hmm. So one thing we discussed in the article was the fact that we have a reference design available, and we discussed this in the article that we can take a silicon onboard charger, and by adopting GaN, we can go and still achieve a 96-97% efficiency, but hit a power density of 3.8 kilowatts per liter. And that value translates over to a lot of places. And this is one of the biggest strengths of GaN, that we're able to operate all the way down from 50 watts up to 5 kilowatts, 10 kilowatt range. And we have a lot of different solutions available for that. That's where we recently released one of our first products for consumer applications, where it's widely being adopted today, having phone chargers with GaN that are more powerful, more efficient, and smaller. When we look at that automotive and EV space, if you step directly outside of your EV, you think about your home, you think about the fact that we're trying to adopt green energy solutions in our home, battery charging, possibly having a battery physically in our home or office building to power our personal electronics, to help with load balancing on the grid. All of those options are going to significantly benefit from a 96+% efficiency power converter. We've done some reference designs that reach 99%. For example, when you stop caring about power density as you do in the automotive market and you solely focus on efficiency, or vice versa when you're looking at power density for that home application, or for example, that phone charger. So GaN has a lot of translations just outside of the automotive space for that, looking at a smaller power density, whether or not it's a consumer product or an industrial product for your grid.
Let me ask a question, Alex. Is this also true for line voltage in Europe?
That's a great question. So
I know that in the US, you have 110, 120 volt. We run at 240 and the three-phase at 380, which is quite critical to get GaN into that playground.
Great question. So I'll kind of tackle it with two different directions. One of, at a system level solution, if you want to continue adopting GaN for a three-phase onboard charger, you can look at a modular design where you independently do an AC/DC rectification for each of your line phases. So you're, instead of treating it like a full three-phase system, you're going to use multiple single-phase. The second approach is going to be doing a stacked FET solution. In that solution, we've actually worked with some customers to look at mixed designs where they're using both silicon carbide and GaN for where they best fit in. So for example, using silicon carbide and a Vienna rectifier for that three-phase AC to DC input, and then from the DC bus using GaN to do a very high frequency up to 1 megahertz switching frequency DC-DC converters. So you're able to mix the solutions to get the best value. And I think that's exactly when we look at Europe. A lot of the EVs coming out into the market today, they're adopting three-phase onboard chargers, and silicon carbide, especially in that AC-DC stage, will bring a lot of value, having 1.2 kilovolt FETs. And then GaN can bring a lot of value in the DC-DC that directly stands off of that, where you're going to want to switch at the highest frequency possible to get that transformer sizing down.
Thank you, Alex. So a question again to Littlefuse. Which SiC power switches lowest RDS on and which topologies are available today in this SMPD package?
So specifically, if we talk about the silicon carbide SMPD, then the topology which are available is the phase-lag configuration. So classical two switches in phase-lag configuration. And talking about the voltage level, those are 1200 volts, and the RDS on level is 20. I mean the classic RDS on level 25 milliohm, 40, 80 milliohm, and 160 milliohm. Yeah.
Okay, Aalok. Thank you. A question again to Hitachi Energy. Is there scope for even larger voltages for high power SiC modules?
Yep, I'll also take that one. So I think there's always scope for more. So we are working right now and to demonstrate. Of course, lab demonstration I think has been done for very high voltages, 10 kilovolt and above. But now we are working on the demonstrating a productization of up to 6.5 kilovolt silicon carbide. So there will be advantages of using, as I mentioned, in traction, but also grid application, especially for very high voltages where multiple devices need to be series to create tens of kilovolts, even hundreds of kilovolts. Going forward, thinking, of course, on the capabilities of silicon carbide, one can think next step would be something like 10 kilovolt. We just need to see exactly what are the packages there, how we create the isolation, clipping distance, and all these requirements. Also the electric fields that we have inside such modules. But we are pushing now the limits of this technology. So as I said, 6.5 as next to be rolled out as demonstrator and product, and the others still in the evaluation phase, especially both in terms of technology, but also in terms of packaging, not only chip but also what we put around the chip to be able for our customers to really use it in applications.
Here we are. That's again to Texas Instrument. What's next for TI GaN?
Sure. So as we were kind of mentioning there, that kind of came up, I guess, in the last question, was looking outside the EV and looking at the larger energy chain that is going to be connected directly to your vehicle. So we're looking at a number of different applications of where we can adopt GaN for either solar inverters, where you're going to have hopefully solar panels on your business or your home. We can help. We've worked on several reference designs initially. They're achieving up to 99.1% efficiency to help you convert from a DC to a three-phase AC signal for the grid locally. We're working on a number of other also one-phase systems, so possibly an energy storage system where you're going to be having a large multi-kilowatt per hour battery sitting in your home, so that way you can charge your vehicle or directly power your home. And then I think one last place that we've also been investing a lot of time in is just looking at other applications. That's where consumer applications have become very common for GaN. When we think about phone chargers, that's a very obvious one that we're talking about today. But you can also think about your TV is something that's very slim, could benefit a lot from GaN. We've been seeing a lot of discussion and adoption there. Another location in your home is going to be consoles, other things that are going to be physically connected that benefit from being very physically small. So if you imagine a small home console, whether or not that's a DVD player or maybe a gaming console, that power supply and it has to be physically integrated into that box. And having that to be smaller and slimmer is going to be something that is very visually appealing, but also brings a lot of value to the consumer.
Thank you, Alex. This is again addressed to Littlefuse.
Mm-hmm.
How can applications benefit from using SiC SMPD in place of standard discrete package?
Yeah, sure. Again, a very good question. So if you, so there is a figure 6 to be precise in the article which we wrote, wherein we have displayed an image so that one can visualize the real application circuit and how the SMPD fits in. So first of all, because of the Kelvin source, you have this minimization of this gate driver loop, wherein also you prevent the feedback of the load current going into the gate. This is one thing. The second is the most of the part of the source common source inductance is excluded, and this actually increases the speed of driving. And with the reduced parasitics, you have also the reduction in terms of overshoots as well as the gate oscillations, so, for example. There was also this figure where we have demonstrated or displayed, let's say if you imagine two things, like one is the TO247 based PCB, wherein you have two discretes as a top switch and bottom switch. And then on the other side, you have an SMPD in which you have a half bridge or phase leg inside. So first is you reduce the component counts first, and the second is if you imagine this commutation loop, then the current has to go back and forth to the top and bottom switch via PCB tracks and so things like that, wherein in these SMPD case, the current will commutate inside the package. So this will certainly give you an advantage in terms of overshoots reduction. Then again, to the specifics to the application, there was an example demonstrated wherein we take imaginary 22 kilowatt active front end rectifier. So one side with SMPD, you can get away with 3 SMPDs, like 3 separate phase legs with that 2-level rectification. And then on the other hand, you need, let's say 12 discretes in order to manage the thermal for that particular rectification. So you can imagine the complexity in terms of thermal management in the discrete case. The second is for the discrete, let's say TO247, you need to mount it with the screw, with the washer. You need to place an isolation foil between the heatsink and the non-isolated tab. So which is additional effort from the manufacturing point of view. The second is if that isolation foil is somehow not placed properly, the torque is not proper, for example, you might have an issue regarding the thermal in the application. So there also SMPD gets you the benefit in terms of the simplified mounting and thermal management. By the way, we do have the application note. So how to mount and the cooling of the SMPD, especially on our website. So this is one thing. The second thing what we observed in that example is there is always a discussion about the RTH junction to case. But if you check the RTH junction to heatsink, which also includes this isolation foil in between, so the non-isolated package tend to have these value much higher than what SMPD offers, because in SMPD you don't need isolation foil. It is inherent isolation, so you can go away with these foil, and because of this you have the higher power dissipation capability for the SMPD. In that particular example, it has been shown that the power dissipation capability is increased by 36% as compared to the standard discrete, and the semiconductor area is reduced by something like 56-57% as compared to those 12 standard discrete. So these are the advantages what you may expect for the SiC application. That was this answer to this question. Yeah.
Thank you, Aalok. We are ready for our next question. So it's a very long one to Hitachi Energy. Are the SiC devices used in the module produced by Hitachi Energy or other producers? Regarding the module packaging, do you see any potential reliability risk related to auxiliary substrate attachments to the main substrate, as they may introduce deformation to the main substrate during soldering process? Will the sintering be an alternative option for the aux sub attachment? Virgiliu,
Yes,
it's your
yes.
turn.
I guess we have the word.
Mhm.
So maybe the first part of the question in terms of external or own devices that we put in our modules. So we have both. So we are buying silicon carbide chips from open market, from suppliers that offer this. I think in the industry they might be quite well known. And we are also producing ourselves. So this comes more recently. Our mother company, it used to be ABB. We invested quite a lot since the 90s in the development of this technology. And now we have really products and chips. So from 1200 volt, as I mentioned, all the way to 6.5 kilovolt. So in our packages now, we go on multiple sourcing. Once is always an internal source, and then as a second source, offering let's say our end customer de-risking of the supply. We offer also external chips. As for the second one, I think we showed in several publications, or at least the high power devices. And I think it goes towards this one, that in order to balance it, we have this external auxiliary suppliers substrate. I have to say, for some packages we have this, for some not. And maybe I let my colleague Slavo comment better on the reliability of this solution. Yeah. As I said, we have both of this. We have packages which have this, packages which can deal without, but there's always as always a compromise to be made. Yeah.
Thank you, Virgiliu. We spend a lot of time on the thermomechanical design, on the simulations and so on, and they indicate that the solution is stable, but simulations are never covering the whole problem. There are always simplifications. Therefore, we finally went for the solution, which is maybe not the best one from the point of electromagnetic point of view, but is still bringing a lot of benefits compared to the simple one-level solution. But there is no risk that delamination is influencing reliability of the module. So even full delamination of the auxiliary substrates is not influencing reliability of the module. So even after that, module keeps full functionality.
Yeah, because also in case of full delamination, we don't have any let's say power dissipation through that part. So it doesn't need to have a full thermal connection. It's just the electrical current flow that needs to be ensured, and this is always the case, unless of course we have heavily degradation like bond lift off and so. But this is the normal, let's say, reliability question that you have with any mod.
Thank you, gentlemen. So the question to Littlefuse: how about the availability of SMPD?
Yeah, so that's again a good question. So as I told earlier, that SMPD was pioneered back in 2012. So maybe at that time, SiC was maybe existing just in the labs. So SMPD is not specific to SiC. The article highlighted definitely the SiC SMPD. However, this this revolutionary package is actually the it defines or simplifies the way design engineers address their power semi integration and assembly. Talking about the variety of technologies, so availability of SMPD as the question asked. So it is available in silicon carbide MOSFETs, IGBT, diode SMPD are there, thyristor, triac, or even their customized combination. The availability of voltage class is from 40 volt to 3000 volt in the SMPD point of view. These are basically available in the standard power electronics building block, such as phase leg, as I said, or a buck configuration, boost, the rectification bridge, or even other customized combinations are also available, listed on our webpage. Yeah, if I go into specifics, let's say for SiC, as I already mentioned, they are available in phase leg configuration. Take for instance silicon MOSFETs. They are so SMPD with the silicon MOSFETs are available in single, buck, or boost, boost plus bypass, phase leg, dual boost. So these are the very typical topology which exist in the power electronics system. The SI IGBT, for instance, those SMPDs are available in the single IGBT or a co-pack, break and boost topology, or even the 4-switch in the one package or phase leg as well. From availability of diode SMPD point of view, you do have single and 3-phase bridge rectifier configuration in the SMPD. Thyristors phase leg are also available. Dual Schottky, dual triac are also available. So as I said, so in terms of SMPD, it's like a platform wherein I mean, there is no way you try to replace discrete or a module with the SMPD, but it is kind of a bridging between these two extreme ends, wherein discretes are typically meant for low power and the modules are for high power. But then there is this gap which we would like to bridge with the help of SMPD. Yeah.
Thank you. To TI, where do you get your GaN?
Interesting question. So with TI, we actually build all of our 600, 650 volt GaN devices in-house. We go all the way from the silicon wafer to the final product in-house inside of TI. We additionally do GaN FETs with integrated gate drivers. Those integrated gate drivers are built, the silicon dies are built inside of TI. And I mean, I guess that's one of the biggest values of when you're looking at GaN and looking across the market of TI ourselves, is that we actually are doing a lot of this in-house. That means when we look at reliability testing, we look at scaling up our production to meet customer ramps, we have full control over that full manufacturing cycle. When we need to get equipment purchased, we're able to own that and control that ourselves and drive that investment, making sure that we're the ones really controlling and making sure that we can deliver. So if you ever have questions about the manufacturing or anything like that, that's a great thing to get in contact with a TI salesperson and learn more about the details about how we manufacture.
Thank you, Alex. Again, to Littlefuse. Are the SiC SMPD with AQG 324 qualification available? Specifically with the dynamic tests like dynamic reverse base, DRB, and dynamic gate stress, DGS.
Yeah, so honestly, I am not really aware exactly about the technicalities of this particular standard. However, you may contact us via our technical power semi support contact page so that we can get back to you with the adequate answer, consulting with our other colleagues. I am posting this link to the chat box where you can, contact us. Yeah.
Thank you. So again to Hitachi. What are the key aspects in designing such a high power SiC module with several tens of individual SiC chips?
Yeah, so I'll give the word to Slavo.
Thank you again for the question. And If I should select one key aspect or one key challenge, it would be, in the case of silicon carbide LINPACK, it would be electromagnetic design. We have several current rating of this module, and for the highest current rating, we are paralleling 40 silicon carbide MOSFETs inside the module. This means 80 MOSFETs in the module, which is challenge by itself. And to benefit from the fast switching, from the low switching losses, we have to achieve fast switching without critical oscillations. We have to achieve balance static and dynamic current sharing. And finally, we would like to have kind of robust design, robust from the point of view, using different setups, using different gate drivers, using even different devices inside. And to handle this, we really needed to pay a lot of attention to electromagnetic design. Of course, we couldn't ignore the other aspects of the module design, like thermal design, reliability, but still the highest priority or the main challenge was electromagnetic design. At least for the module as LINPACK. Could be different for different modules.
Thank you, gentlemen. Question to Littlefuse. What's the next in SiC at Littlefuse? Can you give an outlook?
Yes, we do have certainly the plans regarding looking forward with the SiC in general as well as SMPD. However, it would be we will encourage you to contact us via that particular link which I have posted so that we can answer you in the best possible way for that particular aspect.
Thank you. Okay. The question to Hitachi Energy and what's coming up in regards of SiC at Hitachi Energy? What trends do you see?
Yeah, that's quite a broad question. So what we have, at least at the moment, as I said, we are a high voltage company. So we concentrate on this, the application that we see for very high voltages, as I mentioned, 3.3, 6.5, for different application like traction and grid. As Hitachi Energy, we are very we have a lot of products as a system company for grid application, like HVDC, STATCOMs, SVC, grid quality products. So we do look at together with our internal customers that to see where we can use the benefits of this new semiconductor to improve then the systems that we offer, not only as a semiconductor company but as a system supplier in grid applications. So we look at all these aspects. I think Alex mentioned more on the low power regime, where you look at consumer electronics or charging in and around your home. We at Hitachi Energy, we look at industrial environment, at grid application where big bulk power is being transmitted, generated, converted back and forth from different sources that use this. So we look at this high power application where we see the use case for silicon carbide. And this as a Hitachi Energy company, as our part in terms of semiconductor, we look at these different voltage classes, how we can push always the development in terms of chip, but also in terms of packaging. So how can we make these nice properties of silicon carbide compared to the IGBT silicon? How can we best utilize it? And of course, the packaging are playing here a very important role. So this is where we spend also now resources to see how can the package enhance the performance or keep it and not, let's say, lead to the fact that we have to derate, not use the, let's say, fully, for instance, 200 degrees capability of SiC and so forth. So where can we bring technology developments that we have full benefit of these new semiconductors. So this is where we look at, as I said, high power, and then on going for us, what is for us low power, maybe for others the other end of the spectrum, 1200 volt. We are, of course, looking into using our technology in electromobility, EVs, and charging, and so forth. And I think as other players in the field. So is a bit two-sided. This high booming market like e-mobility, and on the other hand, using this technology in very, very high power application.
Thank you. Now it's the last question coming up.
Mm-hmm.
It's to Littlefuse, maximum possible AC phase current, RMS of a SiC half bridge in SMPD package, limitations by SMD soldier connection or by SiC chips and internal bond.
Yeah. I would like to answer that more in the generalized perspective. So first of all, let's say SiC half bridge, how much current it takes will really depend on what chip is inside, as well as what kind of substrate you are using, like aluminum oxide, silicon nitride, and stuff like that. This is one thing. Second aspect, if we talk about the package limitation itself, then SMPD wide pins, that means I mean to say these particular power pins. So
Yeah.
they are rated at 100 ampere RMS. So that is the absolute maximum capacity coming from the package point of view. And then, of course, depending on the die and this substrate what you put inside, you can have this current out of it. Yeah.
Thank you. Here we go. It's to Hitachi Energy. Can you please share your thoughts on decoupling capacitors and gate resistors in commercial SiC modules? Everyone talks about the benefits of decoupling capacitors, but rarely seen them in any modules. Also, how do you balance the switching losses due to gate resistors?
Yeah, I honestly I'm not familiar with this decoupling capacitors. I know exactly what it means. You know, Slavo? I mean, for the gate resistor is clear for this, as Slavo also mentioned in the design part, is having all these chips together. Sometimes we have to play let's say the compromise between trying to switch as fast as possible to optimize the losses or to reduce the turn-on losses. And so between this optimization between losses and oscillations and inside of the module and outside. But I wouldn't know how this decoupling capacitors plays are also, but I will take it up, and I invite the person who sent this to send us an email, and that we can get back to that. Yeah. Sorry.
No problem.
Yeah.
Nobody can know everything. And the ones who try to do it, sometimes, that's my memory from the past, cheat around. So, gentlemen.
Was it Aristotle that was the last one to manage that, right? So.
Yeah, the technical world has so many aspects, and I will say thank you for that fruitful discussion, and we are all looking forward. Probably some of you will go to Electronica. We will be at Electronica. Our own Wide Bandgap conference will be virtually again this year. We don't want to take the risk in end of November, early December, that all the speakers from all over the world cannot travel the way they want. So thank you again, and
Thank you.
have a great day, and we'll see you one of these days at Electronica or APEC and chat more.